Alrighty, so what I'm gonna try today is kind of a new type of video in which I basically try to solve a problem I haven't seen before live. So maybe that will show you some of my thought process behind solving some of these problems. Here I'm on Codeforces round 636, looking at problem E. So, given an undirected weighted graph consisting of n vertices, m edges, where prices of length m, it is guaranteed that there is a path between each pair of vertices. It's all connected. Might plan a trip from A to B and then B to C. You can visit the same district twice or more, but authorities want to set a price for each road, pays each time he goes along the road. The list of prices that will be used P is ready, and they just want to distribute it between all roads in the town in such a way that each price from the array corresponds to exactly one road. You are a good friend of Mike and want to help him make his cheapest trip possible, so your task is to distribute prices. Choose the optimal path and the price of the trip is the minimum possible. Not prearrange prices after the start of the trip. We have to answer T test cases. So there are under the 4 test cases. The first line of the test case contains between, so n is a number of vertices, and m would be, okay, the sum of the test cases, then 9. Okay, and then I guarantee that the sum of n does not exceed 2 times 10 to the fifth. 2 times 10 to the fifth tells me that this will probably be a n log n, which makes sense considering that this is probably some sort of like DFS or Dijkstra's. Let's see here. So I think the idea is, since we can assign trips, the price to each road however we want, what we can do is, suppose it's just visiting A to B. We would find the shortest path using the least amount of roads, and then use the smallest road, or the smallest cost road for each one along the path. So that would be the minimum cost if it was just from A to B. But if you add from B to C, it becomes a little bit more complicated. Because what happens is that you can, if you go back from B to C, you can reuse the road. You can reuse a road. So like if you take maybe like roads 1, 2, and 3 from A to B, you might also be able to take road 3 from B to C as well, or something like that. So I think the simplest solution would be to just use DFS to find the least number of roads from A to B, then least number of roads from B to C, and then assign it. If any road is doubled, then assign lower numbers to there, assign lower prices to there. But I'm not fully convinced that that is the best solution. Because what I'm thinking is, like, if you, let's just say like the road prices were like 1, 2, 3, 100, 101 or something, and that means, if possible, you'd want to reuse as many roads as possible, because you don't want to like get all the way into those like big numbers. So maybe then it's take DFS from A to B, and then along that path we search for um along that path we search. Not right. If we start a DFS from B, and then use the DFS tree, and we can consider the least or least common ancestor of A and C with that DFS tree with B at the root. Um, would that work? That would allow us to duplicate as many no, but that's not guaranteed to work, right? Because I can already think of a few counterexamples in which it's optimal, or like the DFS tree from B might be different depending on. So DFS might not work just because. Wait, no, it might. Um, so we can start a DFS at A, looking for B, then do another DFS with the entire, yeah, like with the DFS starting at every single point along that path. So that's basically the distance from the path AB to C. And then hmm, that might work. I do have to think about this a bit though. Um, and that you cannot rearrange prices or the. Okay, I'm thinking this solution has merit, I think. I'm just in my head right now. I'm thinking of like proof, maybe like a proof of this. Trying to think of a counterexample for which this might not work. Like the idea is that maybe it's not always optimal to repeat. Like it might you might just want to find like a completely hmm. No, wait, you can probably do some sort of weird Dijkstra. I think you could do some like weird Dijkstra. Um, yeah. Let me try that. Okay, so I think then yeah. Okay, so what we can do then is just start maybe like looking at maybe how we can code this. Let's see here. What numbers are we using? Let's see here. Price goes up to 10 to the ninth. So I might use long longs as default number. And then we have T, we have N, A, B, C, and then we have P. Then to represent the graph, we will probably use some sort of adjacency tree, adjacency list. So first off, for prices, we want this. Then for the graph, let's see here. Or maybe no, that's not the smart. Maybe I'll just use a 2D graph. Um, what is A, B, and C again? Oh, right, the requested vertices. Okay. Then if we're doing a DFS, we probably also want a visited array. If we're doing Dijkstra, we probably want a priority queue. Let's make it a pair. Priority queue, and okay, should be enough for now. Let's write the boilerplate. Let's see here. So we first read the test case. And for each test case, we want to read in the 5 numbers. And A, B, C. So N is the number of vertices, M is the number of edges, and then A, B, and C are those districts. So we clear so what is this? Oh, prices. Okay. So each prices equal to vector. So let's clear it. Prices. How long should this be? It should be. There are M roads, right? So there's M prices. Visited. N roads, and then we have what's it? A graph. A graph is equal to some vector. So there's one for each one, and then finally our priority queue. Or empty? Forgot. I don't really know. Let's just set it to a new priority queue. Okay. Then after that, we read in each pair. So let's have U's and V's to read in for each road. Wait. We read in U and V. Wait. Oh wait, no. We start off by reading the prices. Okay. For how many prices are there? How many roads there are? And then we sort this from smallest to largest. I'm blanking. So dumb. Okay, then we read in each road. We add okay. Cool. So that's everything initialized. We can start off by hmm. We actually just might do a weird Dijkstra's B. That's what I'm thinking. Um, hmm. Oh god, this is a bit harder than I thought it would be. Hmm. So I'm thinking maybe like we go from B and then we like branch out, but then when do we know when to stop using because I'm thinking of now like a counterexample in which maybe you don't take the shortest path from A to B because not taking the shortest path from A to B will allow you to like make a better path from B to C. If anything, it's just think about hmm idea is to go from we use were to use Dijkstra, what would be the transition? Everything is centered at B, so because it's equivalent if we like think about doing a path from C then a path to A. So doing a greedy search from A to B isn't correct. So we have to start at B and then branch out until we find both A and C. We have 2 times 10 to the 5th. We have 2 times 10 to the 5th districts. 2 times 10 to the 5th nodes. So an idea of starting a in general, we might want path from A to B to C to share as many nodes as possible. We can use as least of them as possible. I'm gonna pause this for a moment, because I'm not getting any good ideas right now. Uh, I'll come back when I figured out something interesting. All right, I'm back 5 minutes later. I think I have a better idea. So what I was originally thinking, was kind of do a like start like a DFS from B, and then one at a time go from think about like the maximum what is it called? Max like for each time you go visit a new node, you basically like tell that node, okay, now here you try to find a path from A to that node and a path from C to that node, and see how many like I don't know roads it takes up, and if it's a good if and then record that down and basically kind of just go down the list, doing like a DFS at each node. Obviously, that's too slow, but if we don't think about starting the DFS at that node, instead start off by pre-processing like a distance from A and a distance from C. Then when we do like a DFS from B, we know the distance from A and we know the distance from C. And assuming that like the paths from each node to A and to C don't overlap, then we basically can figure out exactly how much it's costed there and basically go over all like DFS from B over all nodes and then find the minimum such. I think what we can do is ignore the fact that the paths from that node to A and C can overlap, because eventually the ideal solution is going to have paths that won't intersect like that. And if they do intersect, then that means our DFS from B will catch it eventually. So in this case, I looks like I might not even need to use a might not need to use a priority queue at all, although I will need a few more vectors in order to sort of count the deal with like the distances from A and C. So if we think about this, so A dist, B dist, C dist, we can get rid of this probably. And also we probably want in order to find like the max like this type of stuff, what we can do is use a prefix sum for the keys. So a dist could just copy this twice, right? Okay, and then so what you can do is have DFS or no BFS. What am I thinking? Oh, if it's BFS, I definitely have to do the cube, right? It's so dumb. Don't want to use a vector as a cube, but definitely can use a cube as a cube. Hello, Q. What we can do is try to do write a BFS function. So void BFS, in like the number that would be origin, let's call it O, and then the vector distances, right? So what we can do is actually we want to populate all these with -1s just to make sure that we haven't visited them at all. And then we also want the graph, of course, but this is already a global variable, so we can probably get rid of this. So we can just start doing like a typical DFS type stuff. Can't type. This is a vector. I don't know why this is. You know what? It doesn't even matter. I can just return one. Probably just I might delete this. I can just do it later. Um, Actually, is this one indexed or zero indexed? I don't want to mess up accidentally. These are from one to that, so it's one indexed. So let's just make this a little bit bigger. +5 for luck. And then what's going on? Oh, this should be. Oh, that's why. It's so dumb. Wait, this should be fine then. Should be fine. Just forgot what variables I'm using, I guess. And yeah, let's just make these +5s, just 5 for luck. Because these are all one index, and I don't want to accidentally mess up anything. Cool. We can do like a typical sort of BFS. Ooh, we need to think about. Oh no, it's fine. Um, Crap. We want a pair here. So we can keep track of like the current distance. I'm so rusty. I haven't actually done a I haven't done this in ages. BFS, a proper BFS in ages. Um, is it front? It should be front, right? I could probably, yeah, whatever. B for dist. If the distance for the node has already been filled in, we just ignore it. Else, we can do our funny things and BFS. So we first fill in the value. Then or none like next in the graph of node if it's not filled in yet. I don't even need that. I don't need that. Do I need that? I might need that. No, wait. Do I? No, I don't need it. Okay, and then yeah, that's all we need to do. That is a very dirty DFS, I would say. Um, so after the graph has been filled out, we just do a little DFS on A and C. I keep saying DFS, but I actually mean BFS. All right, and then we have a little bit of fun here. Oh, let's do our prefix sum on here first. So let me think. So we already made that, right? Yeah. I don't need this. I'm already filling it in. Yeah. And then oh wait, no, I can't do that. I have to do it outside because this needs to be sorted first. Um, yeah. Okay, cool. And then we consider the distances from B. We want to find the min distance. Oh my god, we are using a lot of variables here. So the min, what is going to be a good number to use for the maximum? Well, the maximum is, let's just say it's the last times like however many there are, right? That's a reasonable amount. Let's just times 2 for good measure. This is definitely too much more the maximum. And then we have our distance from B. We clear it, correct. Okay. So we start off with B, right? So Q dot push. Then let's see here. Just let's just copy this code. We can reuse this. Yeah. And then we could just replace this directly with bdist. Instead, we do this. Okay, so yes, we still need this. We still need this. We still need this. Okay, so while we're on this node, we want to see the distances from A and from C. Um, so total dist is equal to what is it called? A dist from the node, and then plus C dist from the node, right? And then we also have our current distance here. So that means our total distance is going to be 2 times however many, because we're retraversing from here and then traversing new paths here. So all the paths, all the roads from A to the node and C to node are going to have like you're only going to travel at one time. While every single road you're traveling from like B to the node, you're traveling twice because you're going over that road once when you go from A to B, and you're going over that road once when you go from B to C. So we look at the total distance. So let me take a look at the max, or the minimum. So we take the minimum of that and whatever the total distance. Okay. So what we can do, we want to assign the lowest nodes to however these. So what we can do is, so we take 2 times the, like however many nodes there are here, right? Plus any of the remaining ones. So if I can use my brain, please. We've already pre-calculated all of this, so it's just O of 1 excess. Is this it? The problem is, we might get to a point where this is too big, in which case then we don't care about it anymore. Because clearly that's not optimal, right? Let me just use my brain for a second. That's correct. I know we could probably simplify this. We don't need to this. It's just this, right? And we just print it out. Okay. Hopefully that works. Let's copy this test input and check if this is correct. Yes, this does give me the correct answer. Thank the Lord. What I'm gonna do is also add the end line, the new line. so that everything works out. Again. Alrighty. Yep, this seems to be the correct solution, hopefully. So what I'm gonna do is going to hit this, see what happens. 1343. Okay, looking good so far. Accepted. All right, so yeah, that was a pretty nice problem. Yep. Greedy, shortest paths, right? So that's the BFS part of it. Brute force, yep. Sort it, yep. I got this. All right. Hope you enjoyed this type of video.